everyone, and good afternoon, and welcome to today's webinar where we'll discuss design basics for MSE Walls and Geosynthetics. Presenting today are Mike McQuaid from Armtech's Drainage Solutions Business Unit and guest speaker Andy Lister of Tenkata, a global leader in geosynthetic solutions, both of whom I'll introduce more shortly. My name is Janine Yetke, Director of Marketing for Armtech Drainage Solutions, and I'll be your host for today's event. We also have James Carter on the line, who is our technical moderator and who will be running questions and answers at the end of the session. I'll quickly go over some housekeeping items. During the presentation, if you have questions at any time, please enter your questions into the question log. We look forward to your questions, and if we're not able to get your question in the Q&A session at the end of the session, we will respond through email, so please enter your question at any time. As a reminder, attending this session will qualify you for a 1-hour technical informal CPD credit. For those who have registered directly, we will send out the certificate to the email provided upon login. For those who are attending as a group, please compile your list of attendees and send the attendance list with the required details to webinars@armtech.com. I'd like to start off with a brief introduction to Armtech. We are one of Canada's oldest and largest infrastructure companies, supplying a full range of steel and HDPE-based bridge and culvert materials, as well as soil retention and precast building systems. Because of our convenient locations across the country, we are well positioned to serve you wherever your needs are. We also serve numerous sectors from municipal to forestry to transportation and commercial, retail, and residential construction. More about how we service these sectors can be viewed on our website or through discussions with one of our experienced sales representatives. We're also unique because of our centralized engineering departments. We do have the exceptional capability to fully support design and challenging engineered project requirements. Presenting today are Mike McQuaid of Armtech and guest speaker Andy Lister from Tenkata. Mike is a design engineer with Armtech and is experienced with the design of various Armtech Drainage Solutions products, including bin walls and corrugated structural plate products such as multiplate and bridge plate. He also has a specialization in MSE Walls, which he will discuss today. Andy Lister is Canadian Sales Manager for Tenkata Mirify, with over 25 years of experience in the geosynthetics industry, providing solutions to the construction industry and engineering community. He has also co-authored numerous publications related to soil reinforcement systems and is the past chair of the Canadian Geotechnical Society Geosynthetic Division. Today, Andy will start off the presentation with a review of the major types of geosynthetics. He will then discuss the characteristics of geogrids and what to specify. Mike will then cover MSE walls and what they consist of, design methodologies for walls, and will finish up by reviewing specific wall types and facing options. Both of them look forward to plenty of questions, so please continue to enter them throughout the presentation. And with that, I'll hand off the presentation to Andy. Welcome, Andy.
Thanks, Janine, and welcome everybody. On behalf of Armtech, thank you for joining us for this Armtech webinar today. The first topic, as Janine mentioned, we're going to talk from a very high level regarding geosynthetics, the terminologies that you typically see. So the generic terminology of synthetic materials used in geotechnical engineering can include textiles, grids, or more commonly known as geogrids, nets, again more commonly known as geonets, membranes, and composite materials. There's three main polymers used in the manufacture of geosynthetics, and we're going to talk about two of them today. Polyesters and polypropylene, and also polyethylene is typically used. More commonly used is the polypropylene material. It's a tough, flexible thermoplastic material made by polymerizing polypropylene material. It's very similar to polyethylenes, but it's much harder and tougher, more durable. It provides good tensile strength relative to its weight. It's translucent, so it's clear in its normal state, and that's why the majority of geosynthetics, when you see them on a construction site, will look black in color because they have to have a UV stability added to them. Specific gravity of that product is less than 1, so it would typically float. And the majority of these products manufactured from polypropylene are your non-wovens and woven products that you see in the marketplace today. Polyester is more commonly used for reinforcement applications. It's made 85% weight of ester and dihydric alcohol and tetraphthalic acid. They're extremely strong and very high tensile strengths at very low strains, as you'll see demonstrated later in my presentation and Mike's. It's very durable. It's resistant to many chemicals, naturally occurring chemicals. It doesn't shrink or stretch relatively easy, and it's extremely abrasion resistant. It repels water, and it's natural and very quick drying. As you'll see later on, polyester is one of the most common products used to manufacture high-strength geogrids and geotextiles. Geosynthetics. The 4 main types or groups you'll see out there are your non-woven geotextiles. They dominate the marketplace. It's produced by mechanically interlocking. It can be chemically or thermally bonded products, typically called staple fiber non-wovens. Your wovens are your traditional geotextiles manufactured by interlacing 2 or more yarns, fibers, or filaments to create a two-dimensional product. Knit structures more relegated to the geogrid manufacturing process, and they are structures produced by interlooping ends of yarns. And the last type of geosynthetic that we typically would look at, other than the geomembranes, are the geogrids, which is a polymeric material that has intersecting ribs that are joined at junctions that are used traditionally for reinforcement applications, whether it's base reinforcement or engineered structures internally in soil structures. It's important to think of the different types of functions of geosynthetics when you're specifying a particular product. Here are the 5 main functions that a geosynthetic should perform in any given structure. And today, when you look at what we're talking about, we were looking at, traditionally, we're going to look at reinforcement, confinement type of functions of a geosynthetic. As we go through this presentation, you'll see these icons appear beside the different types of geosynthetics we're talking about, which will help you to identify the correct product for the correct application. So when we talk about the types of geosynthetics out there, geotextiles are very commonly known. They're referred to as filter fabrics, construction paper, filter cloth, rags. We hate to see that terminology, but we do get it. So, but they are any permeable textile used in geotechnical engineering applications. What are the advantages of some of these products? When you look at non-wovens, they are traditionally have high flow rates, excellent filtration. They have high elongation, which makes them good for soft soils when you're dealing in erosion control applications, however, not very good for reinforcement. They're very flexible. And then when you're talking about environmental applications in terms of geomembranes, they can provide a cushion and protect your geomembrane liner. What are the disadvantages? Again, you can see these icons below here. They're low strength to weight ratio. In other words, these products are typically not used for reinforcement. They will stretch significantly. Typically, non-wovens can stretch 70 to 100% before they'll fail, which for an MSE structure was not very good. Wovens. Advantages, high strength to weight ratio. They have controlled filtration with certain woven products. They have controlled flow rates. They're very durable, low elongation with high tensile strength, and they're very installation resistant. However, they can have very poor flow and filtration characteristics depending on the types of products. And you'll see in the next slide the 2 distinctly different products that are available. Your woven monofilaments that are available on the marketplace today, they are specifically engineered geosynthetics or geotextiles for filtration and drainage. Your more commonly known products, what we call woven slit tape or slit film products, are polypropylene geotextiles, and they're primarily used for separation. They originated actually from the carpetbagget industry, and they work well as separation, but they have very poor filtration and drainage characteristics. Your high-performance geotextiles, which are the next generation of products, they are extremely beneficial when you're looking at subgrade stabilization and reinforcement, as you can see by the icons there. High-performance woven polyester geotextiles are strictly for reinforcement, where you would typically look for, they can be used in MSE structures. They can also be used for embankments over soft soils. Very high strength products, up to over 1,000 kilonewtons per meter, these types of products. And the last product we're going to talk about, product group, is your GeoGrid group. And there's two different types available on the marketplace. There's your uniaxial products. They can be manufactured out of polyester, as you see here. They can be made out of polyethylene as well. There's also your extruded punch-drawn products, which we call the biaxial. What are the advantages of these products, whether it's polyester, polypropylene, or polyethylene? They have a very high strength to weight ratio, great soil interaction. The yarns are protected for UV inhibitors. And when you're talking about connection strength, we're referring to segmental block walls, where you have to have interaction between the geogrid and the segmental block wall. They have extremely good connection capacity. And again, there's two different types: biaxial, which are typically used in roadway reinforcement application, and uniaxial, which are strong in only one direction for soil reinforcement structures, which is what Mike's going to be covering. What are the disadvantages of these products? As you can see by their structure, they're open structure products. So if you're using them for reinforcement, say in a roadway application, you'd need a geotextile to be used in conjunction with them, so your good quality aggregate does not become contaminated. So what's behind your wall? And I certainly hope it's not this construction fencing. GeoGrids. So we're going to talk a little bit today about the polyester geogrids, but what I'm talking about today can be applied to all various types of geogrids. So why would you look at a polyester product? They're very high strength. They're some of the strongest reinforcement products available on the marketplace. They're coated with a chemical-resistant PVC coating. A wide range of strengths available. For those of you that are new to the industry, LTDS stands for the long-term design strength. And that's the number that most designers will apply to the reinforcement to carry the load of the structure long term. Very durable products available from a contractor's perspective, a wide range of widths as well as lengths in these particular rolls. They're flexible and tough. They provide immediate soil transfer, stress transfer to the soil. They have high long-term design strength. Most manufacturers will have more than 100,000 hours of creep testing. We'll talk a little bit more about this in my presentation briefly, and Mike will elaborate more on it in his. Most of it done through independent testing. They're very easy to handle, no sharp edges, which may injure workers. Most contractors prefer these over your traditional polyethylene type products, just from an injury point of view. They have no memory, so if you're dealing in cold climates, which is what we have here in Canada, these products will lay out flat in the cold. And they're very cost effective. They're creep-resistant polyester fibers. They provide very high allowable tensile strength, minimizing the required number of geogrids in your soil structure systems of it. Why polyester? This is a good graph to show the difference between the different polymers available. So you've got your polyethylene, the red arrow. You've got polypropylene, the black arrow next to it, and then the polyester. And what you're looking at is the strain in that product over a period of time. And obviously, as designers, you're looking for something that has good design strength and it's long-term over a long period of time, typically over 100 years. So this demonstrates, you can see the polyester has very little strain over a long period of time. On the right-hand side, you'll see a bar graph here showing high-density polyethylene reinforcement and polyester, both of equals ultimate strength. However, you look at the long-term design strength, which is the property that you are looking for as a designer, you'll see that the polyester with the same ultimate strength has a much higher long-term design strength, and that's all related to the fact that it is much less susceptible to creep. When you're specifying geogrids as a designer, it's important to make sure that there's been a lot of independent testing done on these products, and most manufacturers out there will have done independent testing. On the right, you can see a pull-out testing of a geogrid. You can see below that creep frames, where they do long-term creep testing on these products to determine that they will actually perform as designed. And you want to make sure that these products have high tensile strength. You want to make sure that they're going to interlock with the soil Most manufacturers will help done testing, and they'll be able to give you your coefficient of interaction and the direct sliding values for different types of backfill materials for these products. And these polyester products are extremely resistant to installation damage, which you'll see later on in my presentation. As well, when you're specifying, you want to make sure that there's both independent and outside testing done on these products. So a lot of manufacturers will have a full complement of geosynthetic testing in-house if they're very committed to the business. They're active in developing and maintaining ASTM standards, so they're trying to move the industry forward. A lot of manufacturers will have accredited labs on site, which is very important to quantify these products and to ensure when they've manufactured these products that they do meet the values that are on their technical data sheets that you are using for specifying. Some rumors versus facts. Polyester geogrids may not be used in concrete backfill soils. I know a lot of times we demolish buildings, crush highways, and we reuse that aggregate and for building these structures, and theoretically they have high pH. Well, a lot of tests and research has been available. If anybody's interested, we can certainly make that research available to you. But polyester geogrids are not susceptible to the pHs of these concrete types of backfill soils. Chemical resistance of polyester. Again, there's been a tremendous amount of work done in research on that. Many studies available. The coating process, the PVC, it's chemically inert to contaminated soils. It's actually impervious to gasoline. And we can have service life for these products of over 120 years for your design life. Independent creep testing. Here again is your creep frames. These products are very high creep resistance. Many manufacturers I've mentioned have over 100,000 hours of creep data, and you need to check with your local distributor or manufacturer to find out what the values they use for their creep reduction values, because even though they're all polyesters, every manufacturer uses different polyester products, combinations, whether or polyethylene, so you need to contact them to ensure that you're using the right creep reduction value. This is just a picture or a slide showing a creep rupture curve from the NTP-EP reports, a number of manufacturers. So you as designers can extrapolate from this and come up with various design lives. Here we have 3 lines, a 75-year line, a 100-year line, and a 114-year design life for the thing. I've outlined the creep reduction factor of 1.47 on the 100-year line. Independent testing, it's very important. It's one thing as a manufacturer to report values, but it's also nice that it's corroborated by independent testing. The National Transportation Evaluation Products Committee is one of the most stringent external testing programs available, and it's a lot of times, especially in the United States, it's required for public and DOT particular projects. This is available, this complete report is online. What's interesting and what's new about this particular program is that they actually go through the entire process, look at creep values, installation damage values as reported by the manufacturer. Previously, they used to look at 200 millimeter lifts with compacted aggregate and moderate compaction equipment. Now they're looking at a more realistic values, 150 millimeter lifts with much heavier compaction equipment to simulate the actual what they see in the real world. These are actual values that are published for 3 of the leading manufacturers in the geosynthetic reinforcement. So you can see here, this is a type 3 backfill, silty sand material, published. You can go online and get these values. You can, based on the testing that's been done, you can see the various creep reduction values. The installation damage values for these various products as reported. These are the numbers that you as designers will actually use when calculating out the long-term design strength of your product. Going back to earlier what I was talking about regarding the creep of these products and the ultimate strength of these. If you are a designer or looking for a product that has to have a long-term design strength of, say, 19 kilonewtons per meter, these 3 leading manufacturers, here's the actual ultimate strength that they would have to start with. The Tensar product, which is a polyethylene product, Strata, which is polyester, and Tenkata, which is also polyester. Based on the research and the independent testing, these are the ultimate strengths that you would need to achieve that 18.9 or 19 kilonewtons per meter. So where I'm coming from is that there's no reason to specify an ultimate strength of a reinforcement material. We see it a lot. It really has no value. It has no place in the design except for as a starting point to determine what your long-term design strength is. There's no reason to specify junction strength or 95% of ultimate. And in past, what has happened, junction strength has been reported as an important property. Many of the geosynthetic, specifically polyester people, have actually cut all the junctions in their particular geogrid, put it into a pull-out frame, and they still have the same coefficient of interaction with their products, just demonstrating that junction is irrelevant in soil reinforcement MSE structures. This is the equation that is typically used for determining your long-term design strength. So here would be a polyester product. You have your wide width reported value. You have your installation value number depending on the type of soils you're using. This is coarse gravel. You then put your reduction factor for creep and then durability. And you come out with a long-term design strength here of 19. The same product, same design strength with a polyethylene, you can see why you need a much higher strength product. You need 143 kilonewton product to get the same strength. And that all relates back to the susceptibility to creep. Great products, however, you've got to address them appropriately in your design. When you're specifying products, there's nothing worse than having your, when you specified a product and it arrives on site, contractors opened up the bundles, and you want to be able to ensure that you can identify the product that's arrived. So it's really important that you have multiple labels on site, whether it's inside the core, on the packaging. Here you can see a typical label. Most manufacturers will label like this. You can, in this particular case, they have tape around it identifying the product. But what happens when you take off the wrapping of that material? It would be nice if you had some form of identification, because a lot of times you're using multiple types of geosynthetic reinforcement. In this particular case, it's actually stenciled on there, so you actually know where that product is in your particular wall. So again, specifying what's important to you as designers. This would be, you know, your wish list. Hopefully made in North America. And the only reason I say there's a lot of good manufacturers offshore. However, when you're dealing on North America, you're typically, if there are issues, they can be resolved almost immediately, and you're not going halfway around the world to determine what the problem is. You're hopefully ISO 9000 certified. They have accredited labs on site, and they also have independent testing and hopefully an NTP evaluation. You want to make sure that they can provide product certification, you have labeling on rolls, and you have identification of the GeoGrid itself in that. Extensive connection data, again, this is all independent. This is more related to segmental block walls. You want to ensure that there is independent creep testing greater than 10,000 hours. You want to have independent testing damage with multiple soil types. And then you want to make sure that the polyester yarns exceed the carboxyl mole and mole weight requirements for polyester, and there are minimum specifications for that. As a designer, you always want to do and/or equivalent, but how do you enforce your specifications? You want to make sure they're thorough. You want to make sure the manufacturer supplying has a good QC program in place, and you want to make sure they also have an on-site. So this is a typical certification that is available that you can write up. And what's key is that the certification shall state that the furnace geosynthetics meet MARV values, minimum average roll, as indicated by the manufacturer. And what is really important is the certification can be attested to by a person. Certification for any product, whether it's a steel product from Armtec, a geosynthetic material, it cannot come from the distributor. It has to come from the manufacturer, whether you're a private label or a branded label program. And here's a typical certification of registration coming from the manufacturer. The person that signs off on this is not unlike a design engineer. They are certifying that this product meets all the specifications, and they can get in a lot of trouble if they're signing a document like this and sending product to a site that does not meet. It's a very stringent program. Here's what you should be looking for when you ask for mill certs. On the company letterhead, individual roles, what their strengths are, what is important to you. As well as you want to ask about their quality control program. How often do they test the product? You want to ensure that they're doing frequently testing and not just running, 200,000 square meters of material and then they test it. You want to make sure that they have a stringent quality control testing program in place. Again, going back to the different labs available for testing these products, delivery and storage, very important as well, well protected. So again, you've seen this earlier, the different labeling as well as on the identification on the roll itself. Alternative materials. It's really important, there's a lot of alternative products out there, but just make sure that you get submittals from the manufacturer and not from the distributor. You want to, whether it's private label or not, that information is available from the manufacturer. As designers, how do you look at requests for alternate materials when you're looking at your GeoGrid? Obviously, there's websites out there. They're very informative. Every manufacturer has a website where you can go in and find information on that product, and most manufacturers will share all types of information that they have. There's the Geosynthetic Specifiers Guide. However, that, even though it is the Bible, this material submitted to this is never audited and it's taken on face value from the manufacturer. So just be aware that even though it's in the geosynthetic manufacturers, they're just taking the information supplied by the distributor or the manufacturer for that. Again, you want to know if it's a private label program, you want to ensure you know who the original GeoGrid manufacturer. You want to look at private label independent testing, the NTPP, which is the most thorough testing out there for these geosynthetic products. As well as ask for the original test data. That's available. It's no secret. Manufacturers will supply that to you for creep, installation, and pull-out from the independent manufacturer testing labs. That information is all available for you to make your own interpretation. And make sure that the CEG and MIL, the molecular weight certificates are also included in that product. And with that, I've completed my section of it. I'd like to introduce Michael McQuaid to the group.
Thank you very much, Andy. This is Mike McQuaid, and I'll be talking about MSE wall design. And what we're going to start off with is we're going to start just a general intro to what MSE walls are and what their components are. So MSE walls, or more formally known, mechanically stabilized earth walls, are retaining walls or grade separation devices. MSE walls utilize a reinforced soil gravity mass to resist external forces, and the reinforced soil is created through the use of horizontal soil reinforcing elements and compacted backfill material. So this is just a typical cross-section of what an MSE wall would look like. The three main components are soil reinforcement, backfill material, and facing units. So your soil reinforcements, generally they'll be the same length. They can be optimized. They can be, typically you could see that they can be longer at the top and shorter at the bottom. And they can also vary in strength as you move up and down the height of the wall. Then you have the backfill material, which works in conjunction with the soil reinforcement. Both these work hand in hand in creating this reinforced soil mass. So it's also a very important component of this MSE wall. And then there's the facing units. Now the facing units, they prevent the soil from spilling out between the reinforcement layers, but they also generally dictate the spacing of the soil reinforcements as well. If need be, additional soil reinforcements can be placed in between these primary reinforcement layers if need be. So just to go into some more detail on the different types of soil reinforcement options you have as an MSE wall designer, the first one we'll look into is geosynthetics. So you have uniaxial geogrids, which I have a picture shown on the top left of them rolling it out. That's geogrids that have strength in one direction, which are generally laid with the strength direction perpendicular to the front face of the wall. And another option you can use in terms of geosynthetics are high-strength woven geotextiles, seen in the picture in the top right. These are often used in temporary retaining walls as shown in the picture. Then there's also another option with metallic soil reinforcements as well. You can use either steel grids or smooth or ribbed steel reinforcements. For the purposes of this presentation, we will be focusing mainly on geosynthetics. So next component is the backfill material. This is just a typical spec pulled from ASTO's LRFD construction specification. It's a pretty broad spec, but it does leave room for the designers to clarify as well. But what you can see with the number 200 sieve, which are generally all your silting clays, you typically don't want anything more than 15%. What this does is this helps to ensure that you have a relatively free draining material, which is critical to MSE walls, as if moisture or water is retained by these soils, you have the potential of additional or unforeseen forces acting on the wall that as a designer you do not want. Typically, you'll want to have granular material. You'll get more bang for your buck with that, and I'll describe that more in detail. And then the other main thing that is very important with the backfill material for MSE walls is that it's compacted. We are embedding reinforcements into this soil mass. We want to make sure that it doesn't come out. We want to make sure it has proper interaction with the soil in order to ensure that we need to have compacted material. And as you can imagine, it's a lot easier to pull Geogrid or any type of soil reinforcement out of loose material compared to compacted material. This is just an example of long-term design strength. This is the calculation and just a few values. And this is more to illustrate that you have to be really aware of, depending on what type of soil reinforcement you are using, that there is a variety of components that come into play when determining your long-term design strength, which you'll utilize in your design. But it also points out when you review the installation reduction factors that these are also dependent on what the backfill material is as well, that these reduction factors can change. So that is something else that needs to be kept in mind, that there is that strong interaction between the soil reinforcements and the backfill material. So just a few things to keep in mind when you're considering, when you're doing the design of MSE wall, for the more forces you have in behind it. Just as a general guideline, generally, if you're estimating how far back or how much embedment you require for soil reinforcement, typically it's about 70% of the height of the wall. Other things to consider on top of just the wall height is the backfill soil and surcharges. Both these components do add additional loads to the wall, which may result in soil reinforcements having to be extended back further, or the strength of which has to be increased. Wall backfill also has to play in the design of the wall, as it allows for the center of gravity of the soil mass to be shifted back and creating more stability. And then, as you can see in this picture, we also have to be aware of where the water table is, as the water can affect the design of the wall, as the water can can create additional loading on the wall. And we also have to keep in mind, if there are changing water table elevations, that we can have some of that water retained in the retained soil mass, and these things all have to be kept in mind when designing the wall. So looking through the analysis of MSE walls now, there's two main design methods that are industry accepted. The first one is the National Concrete Masonry Association, or NCMA. These are typically are more commonly seen in private works and generally seen with segmental concrete walls. And then there's the Federal Highway Administration design method, generally seen for public works, and was developed following the ASTO LRFD bridge design specification and bridge construction specifications. In terms of analysis, like most retaining wall analysis, two of the main concerns that we have are sliding and overturning. So with sliding, with doing these types of analysis, they're external stability analysis, and how we complete the analysis is we rely on the entire soil mass to prevent sliding or overturning. Sliding being having the wall move forward, and overturning is referring to the potential of the wall tipping over. Two other external stability checks that we have to complete as well are bearing capacity and settlement. In terms of bearing capacity, this is something that needs to be considered. One thing to keep in mind, that with MSE walls, the footing of the wall is from the front face to the very back of the Geogrid extension. What this does is allows for a much larger footing, and can allow for these walls to be situated on lower bearing soils. And as well, when talking about settlement, MSE walls are typically able to resist more settlement without damage because of because they are not truly a rigid mass like concrete. And then, as we are considering this wall to be one rigid mass, we have to complete internal stability checks to make sure that it truly does act similar to that. So here's a few different internal stability analysis that we have to complete. We have to ensure that we have adequate connections to ensure that when these soil reinforcements are put into tension, that we have adequate resistance, that it will stay attached to the spacing units, that we do not have to worry about the spacing units falling off. Next, we have tension, which is when we talk about long-term design strength, we're making sure that we have enough capacity in those soil reinforcements to ensure that we are not going to have those soil reinforcements, such as Geogrid, break when the forces are applied to this retaining wall. And then we have pullout. As we are putting these soil reinforcements into tension, we want to make sure that they're not going to be pulled out of the soil. Now, as we can see on the diagram, there is this diagonal break here. What this is generally the internal failure plane of the retaining wall. So in terms of pullout, we want to ensure that the soil reinforcements are extended beyond this line into a zone where they can effectively be, where the soil can effectively resist any pullout forces on it. Just more on the pullout resistance. This is just an equation. I'm not going to go into it in great depth to calculating pullout resistance. And there's a few things that come into play. You have a pullout resistance factor, which we'll talk about more. There's a correction factor. The depth that the soil reinforcement is in the retaining wall comes into play. The length of embedment comes into play. And in terms of C, which is the reinforcement effective unit perimeter, C is generally assumed to be 2 for grids as an example. Generally, what this is implying is that we are gaining friction from both sides of the geogrid. This is also why it's crucial to have separation between geogrid layers to ensure we have this. But the point I need to make here is when we're talking about the pullout resistance factor. Now, this is heavily dependent on, this is an example of what you can use if you do not have the information provided by the manufacturer. So this is just a general overview, but generally your pullout resistance factor will increase as you increase friction angles. So using soils that are more coarse grained, such as gravel, have higher friction angles, which will result in more pullout resistance. Therefore, that's why using granular materials are recommended to be used in MSE walls to be able to gain more capacity out of your soil reinforcements. And then just a few other internal stability checks. We also have to check over turning between geogrid layers or soil reinforcement layers, bending and bulging, which can happen if you have your soil reinforcements spaced too far apart. Typically, it's recommended that they aren't spaced any more than 18 inches or half a meter to ensure that this doesn't happen. And then you also have the potential of shear, where you have essentially sliding along soil reinforcement layers. And then finally, we have compound and overall stability. This is something that has to be reviewed by the site geotechnical engineer. This is beyond the internal and external stability checks and something that can happen as a full site potential failure. Now, generally how this works is, as you can see, there's all these curved lines on the diagram here. These are all potential slip zones where if this soil wedge here is loaded incorrectly, we can have a failure of the entire system, much like you'd have a landslide or an avalanche. So this is something that is very important and something that must be reviewed by the site geotechnical engineer, as it is very dependent on what the soil layers or soil stratigraphy is of the site. Now I'm going to go into some of the different MSE wall types and facing options that Armtech offers. So there's two main different types. There's temporary walls and there's permanent walls. Temporary walls generally have a 36-month lifespan. Two options that we have are geotextile wrapped MSE walls and welded wire mesh with geotextiles. And then we'll go into permanent MSE walls, where we have welded wire mesh with Geogrid Geocell with Geogrid, and bin wall with Geogrid. This here is an example of a temporary MSE wall. This is where it has where it's utilizing a high-strength woven geotextile with a wrap face to create this temporary wall. These are great in areas that in staging for stage construction, where you say have to move a road over or similar applications like that. I'll just go into a brief example of how you construct one of those wrap face, and generally these things still apply to how to construct any type of MSE wall. So first you want to go through, you want to make sure you have a level base, check all grade lines, make sure the wall is aligned as per design drawings. Then in the case of the wrap face, you can place a removable form, and then you can install your first layer of geotextile, and making sure you drape it over the form for what will end up being the return. Then you'll pull the geotextile tight. You want to make sure that these geotextiles are placed taut to ensure that there's no slack in there, so that when they are put into tension, they are immediately being utilized. And then you want to place the compacted material on top of that geotextile. Then we'll wrap the geotextile back, and then we'll cover up, locking that. So and then we'll wrap the geotextile back, and we'll place more material on top. What this allows is for this to be locked into place, so that during construction it is not moved and we don't lose that tension. But it also helps to add some of that separation between geotextile layers to ensure we get that full capacity that we require. Typically, if you have geotextile layers or geogrid layers that are over top of each other, you want to make sure you have at least 75 millimeters of clearance between the two. Then to create your next row, you place another form, you complete what we just did, and then you can remove the lower form and place it on top, and then just continue up the wall. So it's just a repetitive process, and really once the contractor gets used to it, the wall will fly up like nothing. So here's just some pictures of what those temporary walls look like and what the forms look like. They're nothing too complicated, something that can easily be constructed, and it allows for a nice simple wall to be constructed. The nice thing with these walls is if you have to remove the retaining wall, you can regain any of that backfill material you place, and your only loss is the geosynthetics, which is relatively inexpensive. This is another example of a temporary wall where they didn't want any pressure up against its concrete structure. In this case, just because we weren't able to remove the forms, we used a wire mesh form, which we'll look at more closely in permanent walls, to create these temporary walls. And then we used high strength woven geotextiles as the soil reinforcement. Well, so now we'll look at permanent MSE walls. This is a nice pretty picture of a wire-faced wall. This is a project that we did with Armtec bridge plate structure, I believe out in Nova Scotia. So here's a nice cross-section. Generally what this is showing, the blue is the wire mesh basket. Then you typically have the soil reinforcements. In this case, we are using Geogrid, which is going to be located at every basket. Typically, these baskets are 18 inches or 460 millimeters high. So that gives you kind of an idea of how often you have soil reinforcement in there. Here's a few examples. Some pictures. On the top right, there's an example of what the wire mesh facing unit, or sometimes they're referred to as baskets. Not truly baskets, but sometimes that's the terminology. They're typically approximately 3 meters in length. What we see here, this is an example of a rock-faced wire mesh wall. It looks much like gabions, but you can go to much higher heights you can go to much higher heights, and the nice thing with these wire mesh baskets as well is they can be easily modified to go around unique geometry, such as this Armtec bridge plate box culvert. Just to show we can do more than just head walls, here's a nice example of MSE wall, wire mesh facing units with a rock face. And this one here is approximately 7 meters tall, if I remember correctly. And this project was out in Abbotsford, BC. This is another example of what we can also do with wire mesh forms, is we can actually create a vegetated face as well. what has to be done in this case to ensure that we don't have any of the material spill through the openings in the wire mesh is we place a biaxial geogrid with smaller openings that won't allow for the soil to pass through it, but will allow for grass to grow through it. So as you can see, that's what the green material is that they're placing there. And on the top right, you can see what the wall looks like completed. And on the lower right, we see what it looks like after a few years where it has the ability for the grass to grow. So a nice way to kind of make a subtle retaining wall. Another option for MSE walls is we can use Geocell as a facing unit with Geogrid. Geocells, they range in different heights from, I believe, 4 inches high to 8 inches high. Typically, we use 6-inch high geocells in the construction of MSE walls. The soil reinforcement doesn't have to go between every geocell layer, but that will have to be determined by the designer. So here's some examples of them constructing a geocell wall. These geocells, they come collapsed and then they are expanded out. To keep them expanded for backfilling, you put them on a stretcher frame, as you can see here in the bottom left picture. What they'll do is they'll place them in the appropriate areas, and then they'll backfill them with the recommended material. And then you can see in the top right, and then you'll just place the geogrid or the soil reinforcing between these geocells at the specified height. One thing to mention here, we can see in that picture there's a track-mounted machine. It should be avoided using track-mounted machines directly on geogrid layers. Typically, you want to keep it at least 6 inches or 150 millimeters of material over any geogrid before running a track machine. And also, if you are running even tire-mounted machines, you want to try to avoid sharp turns or anything that can disturb the placement of the geogrid during construction. This is another example of a geocell, much like the wire mesh baskets. They can be easily modified to be placed up against unique geometries. And this also highlights the different colors that are available for geocell. Typically geocells, you can get them in black, green, or tan, but it all depends on who's supplying the geocell. And then this is another example of a geocell around another Armtec bridge plate structure. What this picture shows is the unique geometries that you can create with geocells. You can create various slopes and wall alignments with that product. And another picture showing a black-faced geocell. We're also demonstrating that you do have the potential of creating tiered walls as well. And they can be vegetated as well. And then finally, what we'll look into is our the bin wall faced option with Geogrid. Armtec has a product called bin wall. It's another type of retaining wall product. But what we're using in this case is we're just using solely the face of the bin wall to create the facing unit, and then we are extending Geogrid layers behind that bin wall in order to create that soil reinforced mass to resist any of those lateral pressures. This project here was completed in Mississauga. There is a train running over it. The reason why an MSE wall was considered in this case because we had a very limited right-of-way to construct the wall, and by creating this MSE wall, it allowed for the contractor to work within the reinforced area to place reinforcements and compact the material without having to work in front of or behind the wall. And then this is one final picture showing the bin wall space and the geogrid extending behind it, embedded in the compacted granular material. And with that, that ends my portion of the presentation. I'll pass it back to Janine.
Thank you, Mike and Andy. Thank you for your presentation today, and thank you everyone for joining today's webinar. We hope you enjoyed the presentation and found the information valuable. As you saw, there are numerous technical considerations involved in using geosynthetics and MSE wall design. When the need arises, Armtec can help support you through the selection and design process, so feel free to contact us at any time. Mike's contact information is shown on the screen, and he can help answer any questions that you have. Our question and answer period is coming. Due to the time and the high volume of people that we have, we probably will go 5 minutes after. Feel free to continue submitting your questions, and we'll get to them very shortly. First, I'll just go over a few housekeeping items. Today's presentation concludes our Spring 2016 webinar series, and we hope you enjoyed it. In case you missed the earlier two, you can look them up on YouTube by searching for ARMTech, and in the near future, you will also be able to view today's webinar on YouTube. Our fall webinar series will commence in October, so stay tuned to armtech.com for upcoming topics and dates. Please stay connected with us. You can follow us on social media on Facebook, LinkedIn, and YouTube, or on our website, armtech.com. We do value your feedback. We take it very seriously. And at the end of the webinar, there will be a quick exit survey. We would like to know what you think of today's event. Question 6 will ask if you're interested in receiving more invitations for ARMTech webinar events. Due to strict Canadian anti-spam legislation, we are required to have your consent to receive future invitations for webinar events. So if you want to ensure that you're on our invitation mailing list, please choose yes to consent to these invitations. If you do choose no, you will be permanently removed from all emails. So please stay with us. We hope you choose yes. Thanks again for joining today. We will now move into questions and answers, which will be moderated to James. So James, welcome.
Hi there.
Hi, James.
Just thanks to everyone for hanging on there. Can we talk about seismic loads on the wall for stability?
There is sections and I know the HFW code that do address that, and that can be taken into the analysis. Usually that's additional loading. Sometimes it can be simply as just increasing the strength and the embedment depth at the top of the wall, but it can be taken into account if need be in the analysis of the wall.
The key concern with seismic traditionally where it really governs is, as Mike just mentioned, is the upper sections of the retaining wall. And especially in a segmental block wall where you're relying strictly on friction. The wall systems that Mike was talking about today, where you have a complete wrapped face, that the connection really is aspect is taken off the table because you've got a continuous wrap of reinforcement that will not pull out of the face out of the soil mass behind it.
Excellent. Another question, what is the typical self-weight of a panel to be taken? This one reads a little funny. Does that make sense to you guys?
Self-weight. Are they referring to the soil?
I'll just mark that one for a follow-up if it doesn't kind of.
Yeah, I think it'll depend on what system's being used, but yeah, we can clarify that later.
Okay. A few questions about does ARMTech carry triaxial geogrids?
No. Biaxial. Just biaxial.
Okay. Is there any software available for designing MSE walls or Gavian structures?
NCMA has, you can go to the NCMA website, and I think, I'm not sure exactly the cost, but they have their NCMA software that's available that you can download. There is a fee to it, and then the other software that Mike alluded to, which was based on FHWA, there's one program that's called MSEW and RISA. They are both retaining wall programs that are commercially available and that can be downloaded from the internet.
Yeah, there's a variety of commercially available software. Like we have one here. It's produced through Fine. It's a very good program. You can do a lot of different conditions, but there are a variety of different software out there that do specifically look at the code requirements in terms of NCMA and FHWA requirements.
Excellent, thank you. Are there any issues of trees growing in the geocells?
No. In fact, we were just visiting some sites last week in BC, and refer to the retaining wall, the wire mesh, but I was on that Abbotsford project, which has now been in for almost 15 years, and there's actually trees growing out of the front face of that wire basket. So there's no issues whatsoever with vegetation or trees growing out of these retaining wall systems.
Okay. How is GeoGrid connected to the bin wall?
It's wrapped. How we did it on that project is we attached angle onto the front face, and it was wrapped around that angle, and then brought back a certain length to ensure that we had the adequate connections. I believe it was 1 meter.
Excellent. How different, if at all, are segmented retaining walls? I guess the segmented retaining walls are an MSE wall, essentially, are they? Is that right?
Yeah, that's another option as an MSE wall.
There's a few questions about the presentation, so I might as well respond to that because I see them coming in. So we do a couple things. The PowerPoints go up almost immediately, and then what we do is we go back to the original event page and we embed the presentations there, so you guys can refer back to armtech.com/events or navigate to it on the website. And if you look at all past events, anything that's available will be up. The video does take a little bit more time. We do some post-production on that, so it's usually 1 to 2 weeks, and then you can refer back. And also, when you get your CPD emails next week, there'll be links included in those. How does use of geosynthetics or metallic components affect allowable peak friction angle of the soil?
Each one, like, let's say if you take steel for instance, steel is going to have much higher modulus material, so you will need theoretically less steel in there because it's going to provide a higher reinforcing element in the granular soil. So whereas say a geosynthetic, you may need more of that material to reinforce the soil mass. It doesn't change the peak friction angle of that material. It just enables it to carry. It will prevent it from shearing in failure, as Mike was mentioning, in terms of internal.
Mm-hmm. Yeah. So basically, everything has to be taken into account. Obviously, depending on what type of backfill material, what type of soil reinforcement you use. Each case will be different, and these are things that designers are going to have to keep in mind when completing specifications for any type of wall to ensure that the proper reinforcement and the proper backfill material is used to meet the design requirements.
Where you really see that is when you're building, say, a reinforced soil slope. So you take and a lot of times they use native soils. So you may have a native backfill that has a friction angle of, say, 28 to 30 degrees. By incorporating, whether it's steel, if you chose that way, or a synthetic reinforcement, you can now increase the slope angle to, say, 45, 50 degrees, not much more than 50 because it becomes unpractical to build it. But you can now take a soil that would normally be stable at 28, degrees. You can take it up to 45 degrees with the inclusion of these reinforcement components.
That's excellent. Thank you. With wire basket and grid enforced walls, how do you prevent the corners from unraveling over time? Is there a recommended length for keying into parent material?
I'm not sure what they're asking completely. Like if they're talking about ends of walls, if they're talking about the end of walls, generally you step it down. You wouldn't leave it at like a high wall.
You would. It becomes more of an erosion protection. Your geosynthetic will go right to the end of the wall, and then if you're keying it in, it would be keyed into the slope to ensure, or whatever you're keying into.
Yeah.
Now, if you're turning a corner, there are specific details. If you're doing, I guess that's an outside corner.
Yeah.
An outside corner. One piece, you have to have alternate layers of reinforcement on either side. You can't use one reinforcement piece to connect both sides of the corner. You have to have independent reinforcement, and we can send installation details regarding that.
And if we were to design a wall like that, we would provide details like that to ensure that those unique situations are completed properly to ensure we don't have any problems with the wall, whether it's at a corner or at the end of the wall.
Excellent. Another question, is there a source for a design manual or guide for MSE walls?
Yeah, like we mentioned in the presentation, FHWA, they have one, and so does NCMA. So if you go to their respective websites, you can download it. And typically, when you have software too, you have that at your disposal as well.
There's a good question about how to use an MSE wall in a permafrost unstable embankment.
Lots of Geogrid? It can I mean, obviously that becomes a very unique geotechnical question, and as Mike mentioned, you're looking at more than just the internal, so you're going to look at the bearing capacity of that foundation soils, and then you would design accordingly. The beauty is that you may get some settlement in that, and these are 100% flexible structures that can settle a significant amount. So they can be accommodated, but that you're getting into some very detailed geotechnical engineering aspects to do that. But
yeah, and some detailed analysis that would have to be completed with the design of that wall.
And I know Armtech has done a fair number of work up in the permafrost areas in the Yukon with those applications, using what they call a GRS concept to build retaining walls.
There's actually I think there's a YouTube video on armtech.com about specifically about GRS, so you can have a look there. I'll dig that up and share it with everyone on the website. Does the formwork ever rip the geotextile when removing the formwork?
No, generally they're made of, like, you're using a woven material and your formwork is made of something smooth, so it generally just slides right out.
It's typically a flat bar, probably a 3-inch by 1/4-inch flat bar that's going back in there, so it pulls out extremely easy, so it doesn't, you're just sliding it out, so it does not affect the reinforcement whatsoever.
Excellent. We're getting up to about 5 after. So for those who still have questions pending, when we wrap up, there is a survey, and we really love your feedback, so hopefully everyone can take their time and answer the survey quickly. In there, if you have additional technical questions, you can ask them there. Also, number 4, you can basically just say yes or no if you'd like a sales rep to technical rep to follow up with you. And then question 6, Janine mentioned it, but I'll mention it again because it's really important. We really want to obviously be able to continue to invite you to webinars and such. Due to Canadian anti-spam law, if you choose no to question 6, you'll basically never hear from us again. So please choose yes. And finally, number 7, we did add an option to book a lunch and learn for your team. If you've been around Armtech for a while, you probably know there's a variety of topics that we can cover. Obviously, we can cover today's or anything else you might be interested in. So that's question number 7. You can say yes if you'd like to book a lunch and learn. Thanks so much, and we'll be seeing everyone again in the fall. I believe we're starting in October this year. So thanks to our speakers, and everyone have a wonderful weekend.
Yes, thank you everybody, and thanks for joining. Have a great weekend.